Good morning, everyone. We're going to pick back up in chapter 6. So we were talking about the quantum numbers at the end of class on Friday. And so we were introducing the idea that for electrons in an atom, let's try to describe where they're at with a location relating to the size of the orbital with the n value, where n has the smallest possible value of 1. This was like from the Bohr model of hydrogen. The lowest energy level was n equals 1. And then the next highest was 2, so we have these quantized energy levels, being integral values 1 and up for n. And then the angular momentum quantum number is telling us the shape of the orbital. We'll talk about that a little bit later as we go today. But L0 is related to S shape, L1 to P shape, L2 to D shape orbitals. You may recall these. If not, we'll show you some shapes a little bit later. L3 would relate to F-shaped orbitals. And then the maximum n can be, or excuse me, the maximum the L value can be is n minus 1. And so we were starting to think about the range of values last time. There's a slide a little bit later that kind of goes through, like, I think through n equals 3, all of the permutations. But we're just getting into the sense that, like, if n is equal to 1, then the only L is 0. If n is 2, you can have 0 and 1 for L. The range of n and L values is telling you something about the subshell. So like the N1, L0 combinations, the 1s subshell, like the n equals 2, L equals 0 combinations, the 2s subshell. The N2, L1 is the 2p subshell, but we'll get into those as we continue. The range of these subshells, or the range of permutations of the orbitals, is shown through the magnetic quantum number, the m sub L quantum number, and it ranges from minus L to 0 to L, all integers between. And so when we're looking at N1, L0, the only m sub L is 0, so meaning there's one 1s orbital, there's one m sub L for L0, so there's one orientation for the N2, L0, so there's also just an m sub L equal to 0 for the N2, L0, so we're just looking at this L value plus and minus L through 0, so the only m sub L is this one value here, and this is pointing to the 1s orbital, and this is pointing to the 2s orbital. And if we just range this out to one more combination for now, N2, L1, this would have the range of m sub L is minus 1, 0, plus 1, so this ranges in m sub L minus 1, 0, plus 1. So there's 3 numbers here. So there's 3 2p orbitals. So we were just starting to get into like boron through neon as occupying that 2p subshell. And so from the idea of quantum numbers to orbitals to electron configurations kind of start to go hand in hand. So we'll start to see that as we continue. The magnetic spin is starting to tell us how many electrons can go into an orbital. We have spin up, spin down, so we can have 2 electrons per orbital. We see that from the magnetic spin quantum number. Pauli exclusion principle is just telling us each electron in an atom has to be in its own location, if you will. So it has to have its own set of 4 unique quantum numbers. And then those 4 quantum numbers should follow the general kind of rules, if you will, in that if we imagine, like a question that says, is this quantum number possible? So imagine there's a question that says, can an electron have, an n equals 2, L equals 2, m sub L equals 0, and well, that would be impossible because the maximum L can be is 1 when n is 2. And so then you could say, well, what if n is equal to 3, L is equal to 1, m sub L is equal to 2, let's say. Well, that would be not allowed too, because this m sub L is out of range. The maximum m sub L could be is minus L to plus L. So when n is 3, L is 1, the range of m sub L's would just be minus 1, 0, 1. But this is all just leading back to what this corresponds to is the 3, L1 is P. So this is the 3p subshell, and there's 3 p orbitals from the range of m sub L's. And so the m sub L combination is just really trying to tell us how many orbitals are possible in the subshell. So for the 3p, we'd have 3 orbitals within that subshell, just like the 2p subshell had 3. So this is kind of giving us like the p block of elements. There's 6 across. We get a bunch of p subshells. We'll eventually get to the d block. The d is the L2. L2 ranges minus 2, minus 1, 0, 1, 2. That's 5 orbitals. So we get a block of 10 elements across for 2 electrons in each of those orbitals. Eventually we get up to F. F is -3, or is the L3, so you get -3 to +3, that's 7. That's the lanthanide and actinide elements. Eventually we'll get to those. So the concept of quantum numbers will lead into the periodic table. So we can start to see those connections here. And so let's talk a little bit more about the angular momentum quantum number. At least this is kind of summarizing what we were talking about in the previous slide, that this quantum number defines the shape of the orbital. It goes from 0 on up to n-1 integral values. And then the letter of the orbital, the shape of the orbital is designated by the L value. So S-shaped, spherical shaped is the S shape. Like a P-shaped orbital, like a lobe, is the P-shaped, that's the L1. A double set of lobes, we'll see some better pictures in this on a slide, but like a double set of lobes is kind of the D-shaped orbitals. And then the F-shaped orbitals are just having 3 sets of lobes. And again, we'll show you some better pictures. Yes?
If that value only goes up to 3, does n only go up to 4?
Well, that gets a little tricky, you know, like so the we're going to end up talking about shapes of orbitals just basically through what elements in the periodic table, so what stable elements existed in their ground states. You can have orbitals beyond, you know, so you can have the combination of L4 being like, and it just starts to go in alphabetical order here. So 4 would go G, 5 would go H, 6 would go I, but you're not going to see elements in the periodic table using those particular orbitals. So you could see what we call excited states using those, but we tend not to get too deep into those topics. Probably like advanced nuclear physics classes might get into some of those types of orbitals. And I'm sure they would look fascinating too. So we'll talk a little bit about the magnetic quantum number. And this is really just reiterating what we were talking about in the previous slide. The magnetic quantum number describes the three-dimensional orientation of the orbital. And so if you're imagining like a sphere, like the s orbital, there's only like one way to orient a sphere. So it's kind of like, in a way, trying to tell you how many ways might you orient this shape. And then if you imagine this shape here, well, if you're imagining, you know, a p-shaped orbital, maybe it could be on the x or the y or the z axis. Maybe that makes sense that you would end up with 3 combinations for the p orbital. So the range of m sub l minus l to plus l, this is trying to tell you the number of projections that are possible for the given orbital. So we get 1 s orbital, 3 p orbitals, we're talking about 5 d orbitals, 7 f orbitals, so forth. And so this is talking about the range of orbitals that are possible from minus L through 0 to plus L. And then here's a slide that has the shapes of the s, p, d, and f orbitals. So the s orbital, again, it's trying to show us also increasing size increasing n value increases the size of the orbital. So 1s to 2s to 3s, we're just having electron density. And the 3s orbital now further away from the nucleus, so a bigger orbital. And then the shading of the p orbitals is showing us that our probability of finding the electron isn't spherically symmetric now. It's more symmetric about a bonding axis or an axis of the atom. And one way of starting to think about why this might happen is if you're thinking of atoms that are using s orbitals, you get to a point where you might say, you know, is there some space between orbitals that we can use? And that's kind of what the p orbitals are doing. They're trying to find space that's left behind between the n equals 2 and the n equals 3 s orbitals. And so I think, you know, when you start thinking of 1s to 2s, then we see the 2p, it's like there probably wasn't enough space between the 1s and the 2s to have a set of p orbitals. Might be an implication of why you don't see like 1p orbitals. Is you're starting to think between this orbital and this orbital, is there any space that was left behind that we could use for other orbitals? Maybe not. We get to n equals 3, then there was some space in between. So when we look at the periodic table, and we see we go from like hydrogen, helium, lithium, beryllium using the 1s and the 2s orbitals, then we get to the 2p, and we go back to the 3s. So it's kind of just starting to have the atoms just using space effectively and in sort of peculiar ways, if you will, using these p-type orbitals. And so we get 6 elements across the 2p block using the 2p orbitals. And we would call them the px, the py, the pz orbitals, just for which axis the atom or the electrons are residing on. Now, this isn't too, not exactly something that comes up a lot on like calling the orbitals a particular name. And then also it gets a little confusing on, does one of them correspond to the m sub l minus 1 versus 0 versus plus 1? And they're really not defined in that fashion. This is just meant to show you that if you, that you can sort of define the orbitals as just residing on the particular axis. So the px orbitals on the x-axis, the pz orbitals on the z-axis, the py's on the y-axis. And that, ordinarily you're not going to see too much mentioning of the actual names of these orbitals. You might see them a little bit more with the d orbitals, mainly because one of the orbitals looks a little bit different. So when we look at the d orbitals, you see the 4 set of, like 4 lobes, if you will, or 2 sets of lobes. It's kind of like the p orbitals with the second set. But now, if you notice these orbitals, most of them aren't oriented on the axes themselves. They're actually on the plane between the axes. And so you get a dyz orbital that's in the yz plane. Probably the xy, this might be the easier one to see, is if you have this xy axis, the lobes here are in that xy plane, and so we call that the dxy orbital. Not something you're probably going to see talked about too much, but just the idea here that these orbitals are now in between the p orbitals, I think starts to now make a little bit of sense. If we start thinking of an atom, let me just use a little bit of blank space here. If we're picturing a multi-electron atom that's using the 1s orbitals, then the 2s orbitals, and then we had the 2p orbitals sort of next in line for space that's being used by our elements in the periodic table. And then we're looking at sodium and magnesium using the 3s orbitals where they're putting their next electrons. And then if we just follow the periodic table, presumably the next set of orbitals would be the 3p orbitals. And then we get through aluminum through argon. And then our next elements would be potassium and calcium, going back to the 4s. Now, before you go to the 4p, if you're nature, you might say, well, what about this space here? Is there some space here that's like left behind that's not being used? And so that's kind of the analogy to the 1s to the 2s, no real room for 1p orbitals. So we skip, go straight to the 2s, then go to the 2p, because there was some space between the n equals 2 and n equals 3. And then the next question for d orbitals might have been, is there any space here? And there must not have been. So there's no there's no set of d orbitals between the 2p orbitals. But when we get to the bigger 3p, now there's some space in between. So I think this is what nature is doing. It's fighting for space for electrons. What's occupying these orbitals are negative electrons that repel each other, and they're being pulled in by the nuclear charge. So the reason why the electrons even would want to be anywhere near the nucleus is because of the sensing of that nuclear charge. And so it's all about negative being attracted to the positive, but then dealing with the negative repulsions. So we can't just pile the electrons in anywhere we want to. They have to fall into specific areas, if you will, so that they can use space effectively and in a way that is almost managed, if you will. And so we end up with the 3d orbitals between the 3p orbitals. So that's where the 3d start to occupy space. And then we would go across 10 elements using those d orbitals. And then we would get back then afterwards to the 4p. So we'd get back to our 4p orbitals afterwards. And I'm kind of just trying to show the orbitals in like one of the planes so we don't get too confused by 3 dimensions. So that thinking of things in 3 dimensions really gets cumbersome. But we're just here picturing kind of the idea of s orbitals, the p orbitals, and then the d orbitals occupying the space between the p orbitals. Now, if we look back at the d orbitals, there is this kind of like, sometimes we call it like a donut ring around one of the orbitals. It's kind of peculiar. But let's get back to another idea of the L value telling us like how many planes there are of nodal planes, if you will, of like 0 probability of finding an electron. Let's go back to the p orbitals for a minute. So we can sort of define that there's like an entire plane where there's no probability of finding an electron for a p orbital. So there's one nodal plane, or one planar node. So there's like one plane where there's, and a node is just a region of no probability of finding the electron. So we get one planar node, and that planar node is going to correspond to the L value. And so this planar node here is just it's just the L value. It's just the number of that L value. So the p orbitals are L1. They have one of these planar nodes. And then if you think of the planar nodes for the d orbitals, they have 2 planar nodes. So their L is 2, of course. And so that means that they have 2 planar nodes. And so the planes are the planes that bisect the orbitals. So you can imagine there being an entire plane. It's hard to picture, but if you can picture like lobes here and lobes behind, we'd have the plane through the middle, and we'd have the plane this way where there's no probability of finding an electron. And then when you think of this kind of oddly shaped orbital here, you end up with the planes just bisecting the orbital itself. So you end up with like planes that look like this, and so you get a ring around the plane, and you get the other set of orbitals. Not a big detail if you get that or don't get that, but it's just sort of picturing that you get these 2 nodal planes, and then you get this peculiar shape. We call this the dz squared orbital. Now, what this is relative to the p orbital is just an orbital that's using a bigger set of space than the p orbital is occupying. So it's like the p orbital is occupying the space, the d orbital is just beyond the p orbital, and then also bisecting the ring around that plane. And so then there's also a dx squared minus y squared orbital that's also using the set of space beyond the p set of orbitals. So it's just using the space beyond the 3p orbitals for the 3d orbitals. Okay, so orbitals are just trying to find space to use, and not entirely something like we take multiple choice exams, so you don't have to sketch orbitals. You don't exactly have to recognize orbitals other than 1 set of lobes for the p, 2 sets of lobes for the d, the ring around one of them, like recognizing, let me erase this, like recognizing this orbital has shown this as being one of the d orbitals, so recognizing this orbital here as one of the d orbitals is worth recognizing. Now the f orbitals are interestingly not even in our book. So like if you look for this picture, it's not from our textbook. I had to just go scour it from the internet. Not quite sure why, other than these look kind of crazy, because you get a few of them that are exactly like you think. They look like the DXY, the DYZ, the DXZ. These look like the 3 sets of lobes you would expect, and then you get these really kind of peculiar shaped double-lobed orbitals. But these are just orbitals that are trying to have 3 planar nodes, is their characterization. And so again, 3 planar nodes from the L value. And so the S has no planar nodes because it has an L of 0. So the S orbital would have 0 planar nodes. Okay, so a little bit on the M sub s quantum number. It's the 2 electron per orbital quantum number, so it tells you the spin of the electron. And you can think of the spin if you're in a p orbital, are you spinning, this direction, or are you the electron that's spinning the opposite direction? So if this electron's this way, the other electron's spinning the opposite direction. So hard to picture, much easier just to think of that as spin up, spin down. But we can picture spin in an s orbital maybe more easily. If you're thinking of an s orbital electron, maybe you have one electron spinning this way, and then you have the other electron spinning the opposite direction. So if you're spin up, you're spin down for your s orbital or for your p orbital. So every orbital can have 2 electrons through the M sub s quantum number, plus a half, minus a half. And again, not a big detail, but this is with the field, like an applied magnetic field, and this is the spin against a magnetic field. So we're not really defining necessarily the up as the plus and the down as the negative, but it just sort of is showing you that you get 2 electrons. If you have 2 electrons in, say, a 1s orbital for helium, one would have the spin plus a half, the other would be minus a half. If we're looking at the M sub s, say, for hydrogen, where we know we have 1 electron, it doesn't necessarily have to be the plus half. It can be the plus or the minus half. And it's really undefined anyways, unless you have an applied field. When we write an electron diagram, we'll be writing some diagrams. We usually tend to just write that 1 electron spin up just by convention, but it doesn't have to be up. We could have written this way too. But by convention, you'll see it this way just more often. So let's take a look at the summary of sort of through actually n equals 4. So when n is 1, the only possible value is L0. As we're talking about, the only M sub L is 0. And so we just have 1 orbital in that 1s subshell. So the subshell is just the 1s. And then there's only 2 electrons that can occupy that 1 orbital. So we could probably think about the number of electrons too. We get 2 electrons that can occupy that 1s subshell, and the 1s subshell is the entire n equals 1 shell. So when we get to a bigger shell, it makes more sense to talk about maybe the entire n equals 2 shell as being 2 different subshells. It's the 2s and the 2p subshell for the L0, the L1. The range of m sub L for the 2s is just 0. We get the range of 3 values for the 2p subshell. So we get 1 versus 3 orbitals possible in the n equals 2 shell for the for the 2s and the 2p subshells. And then so the total number of orbitals that are possible within the shell is 4 for the 2s and the 3 2p orbitals. So we get 8 electrons into the entire n equals 2 shell. Now, for the n equals 2 row of the periodic table, we get the whole n equals 2 shell. But as soon as we get to the 3, you're going to see that they occupy 2 different rows of the periodic table. So this doesn't exactly correspond to the row or number of elements within a row of the periodic table. So when we get to 3, we have the range of 3 values now for L. We can be 0, we can be 1, we can be 2. And then that ranges from 3s to 3p to 3d. And then our range of m sub L is just 0 for the 3s. The 3 values for the 3p, the 5 values for the d, pointing to the 1 versus 3 versus 5 orbitals. So that's 9 total, 2 electrons each, 18 electrons can occupy the n equals 3 shell. Now, there's so many different questions that and you'll see a lot of practice questions on the quizzes or practice exams, but some of the questions might be, if you have an electron in, say, a 3p subshell, so you just know an electron's in a 3p subshell. And the question might be, can the L value equal 2? Just as like a thought question for the moment. If you know you have an electron in an atom is occupying a 3p subshell, can its L value be 2? Now, I can tell you the confusing part sometimes is, well, the n value is 3 for this subshell, so n equals 3. And so then the range of L's does go up to 2 for the n equals 3 subshell, but this particular subshell specifically is the one with L equal to 1. So as we start to think about the range of values and what the quantum numbers are, they're all linked together. So like when we know we have a 3p subshell, we know specifically the L is 1 for that orbital. Some other subshell, some other electron could have an L of 2, but not that specific electron. So just to start thinking of some applications or questions you might be seeing from these topics, through the 4, we go 4s, 4p, 4d. Now we get to the 4f. And so we have our 0, 1, 3, now 7 possible orbitals. And so that sum together would be 16 times 2 electrons each is 32 electrons that can occupy the n equals 4 shell. So probably the next question, or the thing that you might be wondering is, well, how do you know, or how do elements go in terms of filling into these subshells? How do we go from, we've seen already the 1s to the 2s to the 2p. I think we've seen 3s to the 3p. We've kind of gotten to the 4s and then into the 3d, just kind of following nature. Nature is really what decided this for us, and we're just almost looking to what nature did on the periodic table as a guide. Okay. So when we go from 3D, I think you can kind of see 4p comes next, but let's kind of get to a couple of questions and we'll come back to then when do we eventually get to the 4f subshell? How do the other d subshells fall into place? So how many electrons at most can occupy the n equals 3 shell? Kind of just answered this, but maybe give this 30 to 60 seconds of thought. If you want to compare notes with your neighbor, feel free. So I was looking at this from the 3s, the 3p, the 3d, or the subshells that would occupy the n equals 3 shell, because again, the range of L's would be 0, 1, 2. So we get our 0 or 1 or 2. And then the range of m sub L's gives us the number of orbitals as 9 total times 2 electrons each for 18. And again, this was right on the previous slide, so this may not be a fantastic question for right now since we just saw the answer. Again, maybe we'll just do this one together because, again, this is kind of so related to what we're talking about here. But just to make sure we're seeing for the 3p subshell, so the subshell is like a 3s, a 3p, a 3d. Those are subshells. And so the range of m sub L's for the n equals 3, L equals 1, m sub L would range -1, 0, +1. So we get those 3 m sub L's. Each of the m sub L's could have an m sub s plus or minus a half. So that gives us our 3 orbitals that could take up to 3 electrons being placed into them. Okay, let's get to these shapes here and talk about what we learned from these, what we call probability distribution functions for orbitals like 1s versus 2s versus 3s. This is a way, this is looking at, for a hydrogen atom, kind of looking at the probability distribution of its orbitals. So for the 1s, the probabilities closest to the nucleus. When we go to the 2s, the probability is moving further away from the nucleus. But then we get one of these nodes here. We call this a radial node. Why radial? Because it's on the radius of the atom. If we were looking at this spherically, we would see, relative to the nucleus, we would see that there's a little probability here and then a bigger probability here, and then that there's a region in between those two spaces surrounding the atom of 0 probability. And so our greatest shading, this isn't shaded well because the greater shading should be further away from the nucleus. It would be kind of hard to picture the diagram. But it's just picturing the higher probability is here, and then there's a point where there's no probability that we call that nodal region. So we have a node on the radius of the atom, we call that the radial node. So it's not a plane, but it's like on the radius of the atom, there's an entire point at which there would be no probability of finding the electron. And so we have 0 of these nodes for the 1s. We have 1 of them for the 2s, and then we have 2 of them for the 3s. So when we look at the 3s, we have these 2 nodes. Silly concept to me, but it's just the, if you're picturing from 1, you have 0, so 2, you have 1, 3, you have 2. The next slide will have a question that's pretty straightforward. Actually, one other picture, then we'll get to a question you might see from this topic. This is showing us what the radial probability functions look like for hydrogen, but in other orbitals other than s orbitals. This is a slightly deceiving diagram when we think about some details. This is looking for just a 1-electron system. So you're going to see some artifacts in this diagram that you wouldn't see if you had multi-electrons present. So when we think of a 2p orbital in like carbon, I'm usually thinking of an atom that has a 1s subshell, a 2s subshell, and the 2p goes beyond the 2s. So here, our 2p actually looks to be smaller than the 2s subshell, which is confusing, but this happens because there's no other electrons in the way. So when there's no other electrons, the 2p orbital can sort of shrink in size, if you will. And so our 2p subshell, one of the things we're seeing here is that it has 0 radial nodes. Of course, we might remember that it has 1 planar node by being a p orbital. So we don't see the planar node here because we're just looking for the, along the radius of the atom, that the probability, it's just from the nucleus, it just looks like it's sort of like one of the lobes of the p orbital, right? If we could look this on the way back, we'd start and look the opposite direction, we'd get the shape that looks like the p orbital. Okay, and so that's our 2p orbital, 0 radial nodes. And so the other thing we can see is if you look at the 3D, the first d orbital also has 0 radial nodes. So not a big detail. Not quite sure why this is even worth talking about, but there's sometimes exam questions on this topic, so want to make sure that you're prepared for your exam questions. But the 1s, the 2p, the 3d, the first time there's an orbital within that type of subshell, within that type of orbital, then there's no radial nodes. If we were to look at the 3p orbital, the second of the p orbitals, this would have 1 radial node. And we can almost see it. It's really hard to see, but if we follow and it's hard to see which one's which, but I think this is the 3p, and it has this one node there. So, if you know the 2p has 0, then you know the 3p has 1 radial node. Okay, so what kind of questions might you see? One of them might just be if you had, a question like how many radial nodes does the radial probability distribution function for a 6s orbital of hydrogen contain? Well, this is just coming back to the 1s is 0, the 2s is 1, the 3s is 2, so the 6s would be 5. Again, not quite sure why it matters, but again, a question that you'll see probably on some of the practice exams from the past is asked questions of this nature. So I just want to make sure you see where these questions are coming from. And so then if you had to spot this on a diagram, it would just be growing probabilities of finding an electron further away from the nucleus. So that's 1, 2, 3, 4, 5, and then we'd have the region here. So 1, 2, 3, 4, and then the 5th radial node. And the probability is furthest away from the nucleus, of course, so this is what a radial probability distribution function would probably look like for a 6s electron for something like an H atom. Then another question might be, well, how many radial nodes does the radial probability distribution function for a 2p orbital contain? How many planar nodes? So this would be 0 radial nodes and then 1 planar node. We don't often ask about anything but the s orbitals on these questions for whatever reason, but you can imagine if we said, well, what about a 3p? It would then just have that 1 radial node and then still the 1 planar node. The number of planar nodes, I just want to make sure that we see, that's just from the L value. So the L value is still 1 for a 3p. So there's 1 planar node. We pick up the radial node. Just to go a couple more quick examples, a 4p would be, again, pick up the 2nd radial node and still have the 1 planar node. And just to hit a d, and I don't think we'd really even ask about the d orbitals, but just for brevity, we'd have 0 radial nodes because that's the first possible d orbital. And 2 planar nodes. I don't know what this gets you know what I mean? Like if an orbital has 6 versus 5 radial nodes, does that change something about it? It's, to me, the number of radial nodes doesn't really relate to anything particular about the atom other than just a growing electron density as n goes up, being further away from the nucleus. I think is the only real useful piece of information you get from these diagrams. Okay, so let's get to diagrams. So diagramming out, we've done this already for like hydrogen, usually going spin up. We could have written this spin down, but again, like we were talking about, conventionally we usually just draw it spin up. Helium, 1s2, 2 electrons. Lithium, 1s2, 2s1 configuration. So we get the 2 up and down electrons for the 1s, and then our 2s1. So our electron configuration and our diagrams are just trying to show us the electrons going into the orbitals. Let's picture then lithium to beryllium, just filling in the 2s subshell with 1 more electron. And then when we go from boron to carbon to nitrogen, we're going from the 2p1 to the 2p2 to the 2p3 electron configuration filling into the p orbitals. And then you might start to wonder, how do we fill electrons in? Like when you're carbon and you have these 3 p orbitals, should we spin pair the electrons in 1 p orbital? Or should we pair the electrons into two different orbitals. Well, just think about carbon for a minute. So you have an electron in a 1s subshell, you have two electrons in a 2s subshell, so you have these electrons spinning around these orbitals here, and then you put one electron into a p orbital. Would it make more sense to put another electron into that relatively small region of space, or spread them out using two different orbitals? So I think it makes physical sense that you would spread the orbitals out so that they experience fewer repulsions by using two different orbitals, so that's what carbon does. And then we apply something called Hund's rule. So when filling what we call degenerate orbitals, that means equal in energy. So the orbitals of a subshell are degenerate, like the entire 2p subshell, the three orbitals have the same energy. So when filling degenerate orbitals, the lowest energy configuration is obtained when the number of electrons having the same spin is maximized. So we want to maximize the spin of those two electrons by pairing them together with the same spin, and then spread them out into different orbitals like we have for carbon. For nitrogen, we have three orbitals, spin up for all three, so we're maximizing using all three of the 2p orbitals, and then maximizing the spin. So Hund's rule just says maximize the spin when possible. When we go to oxygen, not shown here, oxygen has the configuration 1s2, 2s2, it's the 2p4 configuration. So we can picture our diagram this way here, 1s2, 2s2, and then our 2p subshell. We tried to maximize the spin, and we have to start pairing for the fourth. So we spin pair the fourth electron in that 2p subshell. Sometimes we characterize the number of unpaired electrons. It's just a convenient question for us to ask to figure out if you have the right diagram usually. So if you have this diagram here, we have two unpaired electrons. So the number of unpaired electrons is often the question we ask. It usually is just something that tells us if you have the proper electron diagram. So then if we go to neon, fluorine would just add one more electron to oxygen's configuration, another spin down, and we pair and complete the shell. The n equals 2 shell is completed by placing the sixth electron into the 2p subshell. And so neon is capping off a shell, and of course that's where our noble gases is getting their stability from, is by capping off a subshell. So they're filled with electrons. They have no room for more electrons or easy electrons to be placed onto neon. Requires an electron to go into a higher energy orbital, hence we don't see neon minus as a common ion. It's hard to remove that last electron because it has added stability. We'll talk in chapter 7 about something called ionization energy. To remove an electron from neon would take a lot of energy due to the stability of that configuration. It ends up being a pretty small atom as well. And so neon caps off its subshell. Something that starts to get useful is counting valence electrons, the outermost shell electrons. And so we might track for some of these guys the number of valence electrons. Valence electrons is more probably useful for like the next chapter, but we're eventually going to get to the next chapter. So let's track the valence electrons. So the valence are the outermost shell. And so for like boron, for example, we have these three electrons are in the n equals 2 shell. That's the outermost shell. So we have three valence electrons here, 1 and 2 for lithium and beryllium. So then carbon would have 4, nitrogen would have 5, neon would have 8. So if you actually look at the nitrogen group, it's like the fifth element across the periodic table, has 5 valence electrons. Everything in the nitrogen group, phosphorus, arsenic, antimony, all would share the property of having 5 valence electrons. So if that's something we know now, then you could look at, let's say the carbon group. You could look at every element, so carbon, silicon, germanium, tin. We could look at, say, tin has 4 valence electrons for the same reason that carbon has 4 valence electrons. That's something later that might help us when we're counting valence electrons for bigger atoms. So if you know the halogens, fluorine, chlorine, bromine, they all share the property of having 7 valence electrons. The noble gases are all capped 8 valence electrons. Sodium then continues into the 3s1 as its outermost configuration. Sometimes we can write this condensed this way. The neon configuration followed by a 3s1 is a way of condensing a configuration. So you can say, well, neon's configuration followed by a 3s1 is another way of writing 1s2, 2s2, 2p6, because all of that information is just what neon is. And then the 3s1 goes back to having one valence electron. So our periodic table is just resetting our valence electron count. So we're just going 1 across and then resetting back to 1 in the alkali group. Okay, now one way we could be sketching these diagrams just becomes a problem with space. If we're looking at, say, lithium, we could have written our diagram vertically instead of horizontally. So when I'm thinking 1s and 2s, it might make slightly more sense if we're thinking 1s to 2s to the 2p subshells having different energies. And if we want to think of energy this way, we might think of placing our diagram vertically. Now, it would make most diagrams just take up too much space. We often don't do this. We usually prefer just to go this way here, but whenever we write the 1s and the 2s, you have to be thinking that our energy is increasing for those subshells. So when we're looking, say, at carbon, that I'm not looking for other configurations, like remember Hund's rule, maximize the spin? Well, can I maximize the spin this way for carbon? And the answer is no, we can't really do that because the 2p subshell just has a higher energy. We can't just be moving electrons around non-degenerate orbitals. We can only move electrons or maximize spin within equal energy orbitals. So that's not possible. So we can't move that electron over, so carbon stays as the 1s2. So carbon might stay the 1s2 because we might be picturing it this way, that there's just a cost to move electrons around, so we're not in a ground state electron configuration easily able to move electrons around. Now, that's going to be violated at some point when we get to talking about some orbitals that are relatively close in energy, and there can be some configuration anomalies. So we're going to kind of like wrap this chapter up by actually spotting some cases where there are some anomalies, but there's no anomalies, like no configurations that aren't what we expect in that group of the p block elements, like in the carbon, nitrogen, oxygen, that area of the periodic table. Okay, so if we're looking at our orbital energies, how do we know these are the orbital energies? Well, one way is that we're actually just following the periodic table. Like this is just following the order of the elements on the periodic table, and we get the 3s to the 3p. We're just using the periodic table as our guide. So if you use the periodic table, you come to the 3p, then the 4s, then the 3d, then the 3p, and then the 4p. And then what comes after the 4p? So once you get across gallium and across the krypton, we get to the n equals 5 row of the periodic table, then we just get to the 5s. So we just go from the 4s then to the 5s, and then what comes after the 5s? Well, what comes after strontium? Yttrium, zirconium, niobium. So we're going across the d block next. So our 4p would then go 5s, then we'll go 4d. And I'm just using, again, the periodic table as my guide here. What comes after the 4p? The 5p. So again, if we get kind of confused, there's a slide in a moment that will have this on a slide where you can point to it. But if you're looking at boron being the 2p, the aluminum group being the 3p, gallium being the 4p, indium's going to start the 5p subshell. So if you get confused, like if you're looking at like tin and saying, should its configuration be like a 4p, a 5p, or a 6p outer configuration, just kind of come back to what carbon is. Carbon's a 2. Silicon would be a 3, germanium a 4, tin would be then filling into the 5p subshell. Okay, let's back up to titanium for a minute. So titanium's just in the 3D subshell. Titanium is right next to scandium, element number 22. So what's its ground state configuration? Well, if we go back to the very start, it'd be like a 1s2, 2s2, 2p6. Gets us through neon, then 3s2, 3p6 gets us through argon, and then we go to the 4s2 for 2 electrons, again following potassium and calcium, and then we go back to the 3d in terms of a number, we go down to 3 for 2 electrons into that subshell because it's the next 2 electrons titanium has to fill into it. And so again, I'm just kind of using the periodic table as my guidepost here. This could have been written as argon. So we could write this as argon 4s2, 3d2. How do I know this is 3d and not 2d or 4d or some other number? Well, it's the first d subshell, and the first time we can have a d of L2 is when n is equal to 3. So sometimes it's a little confusing that we're filling into a 3D in the fourth row of the periodic table, but that's just how nature determined the order of the elements for the D subshell. So how many unpaired electrons do we have? Well, this just requires us to think about the placement of electrons into our orbitals. So if I have my 4s, my 3D subshell, 2 electrons into the 4s, 3D, I maximize the spin, use 2 different d orbitals, and maximize the spin. So I have 2 net unpaired electrons. Like all of these electrons in argon are spin paired. Spin paired just means a spin up and a spin down in the same orbital. So we have a spin up, spin down. These are spin paired, and these are spin unpaired. The valence electron question can start to get confusing because now we're filling into like 2 different shells, right? Like what's our outermost shell? So the outermost shell would be the 4s for 2. So for sure we have 2 electrons that are in the valence shell from the 4s subshell. We're going to add any electrons in an unfilled lower subshell. So like we haven't capped off that 3D subshell, so we're going to count those 2. So we're going to come up with 4 valence electrons. Valence electron counting, for some reason, isn't a big detail in Chapter 6 that other instructors agree on testing on. I think it's important that we count these and know these. It'll help us in later chapters where we start to need to know how many valence electrons an atom has. So you probably won't see a lot of questions getting at the valence count, because it does get a little nuanced of when do we stop counting, or like we count the 4 because it's the outermost shell. I think counting the 4s2 makes sense. But then the 3d2 I think also makes sense because we haven't filled that d subshell. It makes sense to count those. But then what about the 3s and the 3p? Well, it doesn't make sense to me to count those because they're already filled. They're in the lower energy subshell. If we fill the 3d, if we get all the way to zinc, if you look at zinc's configuration, zinc would be an argon 4s2 3d10. It's all the way across the D subshell. Let me also mention, if you add up all these electrons, like the 2 for titanium, 2, 6, 2, 6, 2, and 2, that should add up to titanium's number of electrons as a double check. So titanium is element number 22, should have 22 electrons in its ground state configuration. Let's do this with zinc real quick. So zinc is element number 30, so it should have 30 electrons. We have 18 from argon, because argon's element number 18. 1s2, 2s2, 2p6 gets us to 10, and then 3s2, 3p6 gets us 8 more for 18. So plus 2 here, and then plus 10, that's 30 total. So just making sure that we see like a quick double check for our configurations is just simply adding up these electrons here and seeing that we match the total that we should have. And so now for zinc, we fill the 3D subshell. I think it makes sense to call zinc, determine that zinc should only have 2 valence electrons because it just has these 4s2 outermost shell. The 3D is completely filled. Now, why this matters to me is only because our book and our notes had identified zinc as only forming the zinc 2 plus ion. And this is kind of why. That the 3D subshell, those electrons remain locked into place. We're not going to easily remove those to make a cation. When we get to cation configurations, that's next chapter. But next chapter, we're going to see that these are the electrons that are lost to make a cation. So like configuration to cation configurations relates right back to nomenclature that we learned zinc only forms a 2 plus ion. You start to see the reason why atoms like titanium could form a +2 or a +4 cation or multiple different charge states is due to the fact that it can lose the D electrons or can lose the S, all of them, some of them. That's why we get a lot of different charge states that are possible in the transition metal block. Okay, so takes us through zinc. Which atom has this configuration? So what if we give you a configuration, can we determine the atom? So 1s2, 2s2, 2p6, 3s2, 3p6, all that's argon, 4s2, 3d6. You guys see how that just has, that's 26 electrons assigned? You guys see quickly, we're just looking for element number 26. on the periodic table. Or we're looking for the element that's 6 across the D block. That would also be element number 26. That's iron. So we can give you a configuration. You can tell us the element. We can give you the element. You can give us what we call the expected configuration, kind of following these base rules. What about tin? So we mentioned tin. Let's actually answer one of these questions right off the bat. Tin is in carbon's group, so it should have 4 valence electrons, just like carbon does. So this is as simple as saying it's in carbon's group. Carbon has 4 valence electrons, so too does tin. Tin's configuration now is just following the krypton configuration. I'm sorry, it's following the krypton configuration, which is 36 electrons. In my head, I said 5. I didn't write it. 5s2. So when argon 4s2, so krypton goes then 5s2, 4d10 all the way across the D block, and then we go back to the 5p for 2 electrons. So everything like lithium, beryllium to carbon was 2s to 2p, sodium to the next was 3s to 3p, potassium, calcium on across to the p block was 4s to 4p, so now we're just going 5s to 5p. And so then what's the valence diagram? 5s2, and then the p orbitals. Now, we could show the d, but they're not really part of the valence. But if we want to show the d, it's just 5 orbitals all spin paired. If you were bothered that I didn't go 5 one direction and then 5 the other, it's just to save time that I did it that way. So you could think 5 go up and then the next 5 go down. However you want to picture it, we end up with this diagram. So those don't count towards the valence count. These are my 4 valence electrons, with a net 2 of them being unpaired. This was a slide I was kind of referring to earlier, that we had a slide that has some of these numbers shown, where the 2s, the 2p, the 3s, the 3p, 4s, 3d, 4p is shown. And then the f's are wedged in. This is really helpful, and it really makes it clear for us to see we go 5s still across the 4d, then the 5p. And the way you can know this, even with the periodic table sketched this way, and the only reason you see the periodic table the way we do it is space filling. If you just take the f and remove them and put them below, you can wedge the periodic table together so you can make the font size bigger on the table. Imagine we wanted to print this in like a book. Like, how small would all the elements be? It'd be really hard to read. So we just move the f below the periodic table for space filling reasons. This would be a much better way to write the periodic table and just use like this. Like, we had room. We should just put the f electrons in there. It would have been much more intuitive to see the f block, because then you can see you go 6s. So the 6s is cesium, barium, and then lanthanum is shown what looks like in the D block, but then we go cerium, praseodymium, neodymium down across the bottom row of the periodic table. And so we end up going the F block next. Now, why 4F and not 3F or 5F or some other number? Well, the first time you can have an F is L equals 3. The first time you have an L3 is N4. So 4F should be the first F block. So we get our F block, and then we come back to the D block. So once we get across the F block, then we come back to the D block, then we get back across the 6P, on way to the 7S, to the 5F, to the 6D. So the numbers just kind of fall accordingly. We don't do a tremendous number of examples of lanthanide and actinides. They're not the most useful elements like in a chemistry class. Usually you don't want to work with uranium samples too often. But this diagram here, this will carry into next time a little bit, but here, if you look at the actual configuration that you see, these are all exactly as you expect in what we call the P block. So the P block configuration's all exactly as we expected from these rules that we've been putting into place. The S block, all exactly as we expected. We do see some configuration anomalies with things like chromium. We see a configuration anomaly with copper in the first row of the periodic table. And then we see some configuration anomalies in the second row. So we do need to talk about that a little bit. I don't think there's enough time left today to get into it, but we do see what we call some configuration anomalies. And there's a few of them in the 3D, 4D, 5D blocks, and there's a few in the F, the 4F, and then the 5F blocks. But there's none in the S or the P block, what we call the main group elements. So there's no anomalies, no configurations you didn't expect in the S and P block, and then there's some in the D block. But we'll talk about a few of those, and then we'll wrap up, I think really just one more example from chapter 6 after that discussion, and then we'll go into a couple more slides here, just some not review topics. A couple of uses of chapter 6 are in the remaining slides, and we'll get into some review problems starting Wednesday into next Monday. So we're about to the point where we can start reviewing for midterm 2 on Wednesday. So I'll put a review packet up, email that out to you guys here soon. So look forward to that. All right, thanks for the attention today, guys. Have a great day.